it looks like the Poisson ratio will vary as a function of stress, but what it really happens in this case is that as we approach failure, elasticity does not work anymore. Let's add one more plot over here. Something I forgot to mention in the lectures, which is volumetric strain. Volumetric strain tells you if the rock is either compacting or expanding. And volumetric strain is going to be equal to the summation of all strains. In this case, the axial strain plus the lateral strains. And since we have two lateral strains, I'm going to multiply the radius strain times 2, and that's going to be the volumetric strain. I don't know if you know this trick here, right? But if you find there the dot, double click, that will copy that for the entire interval. So, let me see if I have 4 or 2 plots here. No, I have 2. So I'm going to use the same trick here. Control copy, Control V, and I'm going to move this one over here. And now this one is a volumetric strain. Elasticity, it tells us always that we are in an elastic part of the curve, and in theory, if we have compression, the rock should always get smaller and smaller, and that's why this curve is always getting more into the positive direction, right? It's always going like this. But when you get close to failure, notice that the curve kinks back to the left, telling you that there is an expansion. That's the point when the rock breaks. When the rock breaks and your fracture opens up, that makes actually the fracture bigger than what it was before at that point. The opening of a fracture requires some volume, and that's what it makes the rock expand at this point. And that's the volumetric strain. So if you were to compute Poisson ratio around here, it will give you 0.5, which doesn't make sense. If you were to compute the Poisson ratio in this region, it will give you a negative Poisson ratio, which it doesn't make sense either. So that's why you have to compute the Poisson ratio in this region of linearity of the strain stress deformation. So I'm going to let you work on this for 5 minutes. Okay, probably you won't have all the time to solve it, but if you have any questions, just let me know. I just want to tell you that very likely in the future, you're not going to be computing all of these Young moduli, but you may receive from other service companies measurements of Young moduli and the reports of what you see over there. Yes?
So the reason you put the legs, I want to call them, on there is because that's the region you want us to calculate in? Or am I interpreting that correctly?
Say again? I didn't get it.
There's like these 2 little legs, like of data, like it splits.
Oh, okay. These ones?
Yeah.
These 2?
Yeah, what are those?
No, those are unloading lines. Let me explain this over here. So usually, if you were to do a simple test, you will load all the time. This is the direction of loading. The stress is always increasing. However, sometimes we conduct tests in which we do a loading, but at some point you do an unloading because we want to measure the unloading modulus. We're going to see later on why this unloading modulus is important. And then you load again, and you continue loading, and then usually you do that a couple of times, and then unload again until failure. If you compute the Young modulus over here, which is what I am asking you, that will give you the loading modulus. If you compute the Young modulus right here, that will give you the unloading modulus. And the unloading modulus is greater or equal than the loading modulus. Yes?
I came in late. How do you open the file?
So, let's go one more time to that, okay? So, you come here. You go data, import from text, and you look for the file that you downloaded before, okay? And then you go import, and here you choose the limited, next, tab, tabulated, next, finish, okay? And then you get it, okay? Okay, all right guys, I'll let you work on that. A minute, let me know if you have any questions, okay?
Do we have questions for the I need to put in a file real quick. That's something that I'm going to do right now. So for the homework to do at midnight tonight, when I did TBDSS versus MD, I created, like, I changed TBDSS into TBD so that I wouldn't have like negative depth. So like, do I still label it TBDSS? Okay. So when I did like my bulk density, I also used that same like, linear fit in order to find like a TBD at like the different MDs we were given. And then for this one, does that look right? So like, okay, actually I do have a specific So,
I prefer that you go everywhere. Well, so with that, you can use that.
my equation is backward. Basically, I did 0.44 times the depth of water plus, and I assumed that all the rock at this depth and above had this density that I reported. But when I did the next one, I did like this previous one plus an average of these two densities.
The density is going to be 2 for everything above.
Okay, so then, okay, wait, awesome. So for this then, I can just, instead of this, say 2.
No, it's not separated. It's very similar.
Okay,
You can,
so that changes it. So, but for this one, I take the average.
it's called separated. But
The average, and then I just add it.
you can open it all.
So I said like it's the average for
Just need to
the distance
specify
between these,
limits.
and then I added it to the previous. And then for PI time, like I did split it up, but like technically it's just 0.44 times the entire depth, right?
No. Because the aquifer doesn't start until 30.
Right.
So the water level goes, so you have to subtract the depth minus 38, because you don't have water from the surface of the river.
No, so we know it's kind of like more pressure will know.
So flow pressure is going to be, this is where the water level is, it's going to be like a straight line like this. Now this doesn't start at the surface. It starts at minus 38. So you just take that minus 38 and you just multiply by 2.
Oh, so we don't have to worry about like, there being anything here at all?
Well, because you know there's no water. There's no water.
I thought for underneath
No, this is an
Well, that changes a lot of stuff.
So when you go like from 0 to 38, you only have rock making.
So when I did this, then, and I just pointed it 4 times my 38, that was wrong for my estimate.
I guess you don't need that.
So we don't need that? Okay. So,
But we
I
need-
keep this minus 38, it's just like,
I mean, you're looking at SD.
yeah.
Why do you want to include water? Like, why do you want to include water in this? So what's the equation for SD?
So what I would do in this case would be, I would look at the 2 points
What's for the
where I want to make that.
In 38, it's 2.
No, like everywhere. Yes, so it's like all the way to the surface. It's 2.
Yeah, let me show you here.
2 over 8 and 2 over 8 until the first value they get. I think it's going to be 1 equal. So it's going to be rho GC, that's 2 times G times C.
Okay. The first one, then I take this out.
Okay, guys.
2 times.
Yeah, sorry.
One more thing over here before we go to the next problem. I'm asking you here to
Thank you.
compute the young modulus doing a linear fit, okay? This is not eyeballing. Although I like very much eyeballing all the time, just tracing a line. Here you have to do it with a linear fit. So you're gonna have to select a range somewhere over here to do that linear fit. So let me bring this one back to axial
I
strength.
changed the only values to it.
And now it's that curve, right? But you see that one goes from 14 to 2,891. Well, you have to find the interval. I'm just gonna make something up here, like 1400 to 2000, in which I want my data, okay? And that's gonna be just that interval, you see? I changed the selection interval, okay?
Where did you chart one?
I changed instead of going like select data, all of that, you just can change it over here on the top. So let me iterate a little bit and see if I find it. So let's go 600. No, okay, wait. I'm
1600.
yeah, 16 and 16. Okay, that sounds pretty good. And then I'm gonna go here with, let's say, 19. Okay, I got it right there. And then you add the trend line and display equation chart, linear, and there you get your Young modulus.
What's the end of it?
So your Young modulus here is 0.61 million PSI in that interval.
We don't need that.
That's what you have.
38 times 4
Okay?
Wait, what?
Is that the correct range, or was that just an example?
No, this is just an example. But you're gonna get a very similar value, okay? Okay, guys, let's go to the next problem because I want to talk about the homework which is due today a little bit because I know that many of you have questions about that. So let's see. Next problem is it's easier. I'm asking you here to plot what are positive and stresses in this cube. So now this is just a 2D example, but now this is the orientation of the coordinate system. Do you guys remember the rule of the right-handed coordinate system, right? Always the right-handed coordinate system, and this is going to be particularly important in 3D, is that the first axis is your index, second axis is the middle, and third axis is your thumb, right? So first you should check this right-handed coordinate system. X is going to be 1, right? y is gonna be 2, so it's like that, and 3 is going into the board. But in this case, we're not interested in 3, but we know that 1 and 2 are oriented as they should be. Okay, that's the first thing to do, to check that. And once you check that, you have to find here, you have to draw what are positive stresses. So do you remember what we said about positive stresses? Should they be compression or
Compression.
compression, right? And they should be always pointing down or pointing towards the element. That what compression will be. So in this case, compression in X will be like this. Compression in Y will be like that. That's going to be positive. And what is a little bit more difficult is the shear. And for the shear, let me come back here to the paper. So we have X, we have Y. What I'm going to do is I'm going to use that rule that I was telling you about the positive and negative phase. So you walk a positive amount, that means in this direction in X. And if you walk a positive amount, you will get to the positive X phase. If you walk a negative amount from here, you will be on the negative X phase. The same way, if you walk a positive amount in Y, this one is going to be your positive Y phase, and this is going to be your negative Y phase. Compressions, we said, I'm just going to do in X. It's going to point towards the element. This is going to be a compression. And if I wanted to write a compression shear stress as I go on the positive phase, should this one be pointing up or down?
Down. Oh, wait.
Up or down?
Wait, what was the question?
Shear stress.
Oh, then,
The shear stress in order to be positive.
Down.
then.
Oh, shoot. Up.
Up. It's gonna be up, because remember, in the positive phase, the arrows point opposite to the coordinate system. Like this one,